Good day. Welcome to Exida's webinar. Let me just check my status screen. Turn off the phone, and we will get started. Welcome. I see we have a good group of people out there, and others are still joining. I'm just watching the screen, but we're going to go ahead and get started anyway, because a lot of the material up front is a bit of an introduction. Failure rate analysis paralysis. I'll tell you the stories about how challenges have arisen over the years and how we've dealt with them in my work at Exida. You understand that failure rates are a function of a number of different variables. Let's take a look at the key ones and figure out what we're going to do about it. If you don't prioritize and figure out how important they are, you can absolutely spend a lot of time on an FMEDA. I've honestly heard stories about engineers that would take 1 or 2 months to do an FMEDA. And of course, the engineering manager, who's responsible for cost and schedule, is not happy. So let's see what we can do about this to optimize the FMEDA process. My name's Bill Goebel. I work for Exida. We were founded in 2000. We do a lot of work around the world in functional safety, alarm management, and automation cybersecurity. We have 3 business groups: an engineering tools group, a lifecycle services group, and a certification and assessment group. I'm talking to you today from the engineering tools group and the group that has developed FMEDA tools and the component reliability database. We do consider ourselves a knowledge company. We do research. We publish our research in books, training courses, webinars like you see today, and databases. The certification group does functional safety and cybersecurity certification in using a wide number of different standards around the world. And we're quite pleased that a market study done in 2015 by the Automation Research Corporation, ARC Advisory Group, concluded that Exida was the global leader in device functional safety certifications. And we're quite pleased with those results. The engineering tools group at Exida does a number of tool suites. One of them is oriented toward the systems level design called Excellentia. There's a corollary tool to gather up field failure data, which is important to our discussion today. That tool is called SILSTAT. And there's another set of tools, a suite of tools called OEMX for use in product development. Functional safety was the driving factor for the development of the FMEDA analysis process, which required a failure rate component database. I can tell you all the stories about how it got started when I created it back in the late 80s with a number of other engineers now at Exida. But we're going to skip over most of that story. You can look that up on the internet. Functional safety has 2 fundamental concepts: a safety life cycle, which is a detailed engineering process intended to reduce design errors and documentation mistakes. The other fundamental concept is probabilistic performance-based system design, where we wish to deal with the inevitable quantity of random failures. It's a great system. Actually, it's ingenious in my mind. It allows risk optimization. But how many random failures, and how do I meet the performance criteria from IEC 61508, ISO 26262, and all the other functional safety standards? FMEDA is the answer, and we'll talk about it in detail today. Of course, the safety life cycle concept starts with an engineering process. I'll just mention briefly that the engineering process is created by engineering management for the purpose of reducing design mistakes and creating documentation needed for functional safety and cybersecurity certification. The objective of any process is to find errors and reduce rework. Therefore, increase product design quality and reduce the schedule and the cost by reducing rework. So that's concept number one in functional safety. As part of that development process, there is hardware design. And if the hardware design process is done well, after the design is created, an FMEDA is performed and followed up by fault injection testing. I mentioned we're talking about a component database, and I mentioned FMEDA because, in fact, FMEDA is the most common way of showing metrics that meet functional safety requirements. What is this? FM, failure mode, effect, and diagnostic analysis. It combined a number of techniques, including part stress analysis, pioneered in the 1970s, the FMEA systematic review procedure, diagnostic analysis, and failure modes. Combine all those things together into an analysis technique to give us what we need for a number of reasons, including functional safety. When components from a design are chosen with specific application parameters, we take that information and look at the failure rates and failure mode distributions provided by a database. Diagnostic methods are chosen if any automatic diagnostics are part of a design. Given that set of information, the components, the failure rates, the failure modes, and the diagnostics, we can do an FMEDA. The failure rates, the failure modes, the diagnostic coverage, the useful life, and even proof test coverage, if that's applicable, for each subsystem can be predicted if we have a good component database. And I'll just lastly, the FMEDA method was created specifically for three things: to identify design issues, to provide predictions of field failure performance, and to allow practical implementation of functional safety compliant products. Practical is the key word. FMEDA provides the metrics needed by the functional safety standards to show that any particular design meets performance requirements of a given ASIL or SIL level. The key is the component database. The level of detail in any component failure rate database will change the results. Those of you who are reliability experts, you know this. The question is how much and what is optimal? And by optimal, I mean engineering hours invested versus accuracy of results. There are many things. Well, let's focus on electronic components. There are many things that impact the failure rate of electronic components. Those of you who are experts kind of recognize these stress factors on the right-hand side. Temperature, temperature changes, humidity. Of course, they're kind of in the priority that my experience dictates. Perhaps altitude should be raised higher given soft error events, depending on the diagnostics, of course. Now let's look. Physical materials of the component and the component design. That's the responsibility of the component manufacturer. Those of you who are designing products know that you must pick the components that are suitable for your design and your intended application environment. Your design also has a major impact. The product design, especially relating to self-heating of the components, and product design related to exposure of stress, electrical stress, shock and vibration. How strong have you made the product design? And product level design related to ambient temperature and temperature changes. Then the rest of this is out of our control. Your customers and the stresses in their environment, the magnitude and frequency of the temperature cycles of your application, constant use versus periodic use, and operational and maintenance practices. Now I want to just focus a tiny bit on this last one, operational and maintenance practices, because it's something reliability engineers really do not think of. And after studying literally thousands of field failure reports at exida, we noticed something was going on. We found that the failure rate of the exact same manufacturer model number changed from site to site. So we did a very detailed study in one company where different sites allegedly followed the same maintenance practices. And of course, we found out that they didn't really follow the same maintenance practices at all. And the failure rate changed between 4 and 10 times, depending on the product type. How susceptible is the product to maintenance-induced stress? Well, think about all the variables we've discussed, and we have to ask ourselves, how do we deal with all these variables? I mean, you can get yourself so wrapped up in the level of detail that you can't even, you choke. You can't even generate a failure rate prediction if you get so wrapped up in it and think about everything all at once. So how do we move? We prioritize. Failure mode and effect analysis is done with, we start with average failure rates for a fixed set of environmental parameters. Let's start right there. What do you mean environmental parameters? Well, we'll create a set of environmental profiles that are characteristic of different applications and pick an entire profile. Done. We have all the environmental variables defined. We'll come back to this later. And then we go about building an electrical component reliability database. We know that for an FMEDA, obviously we need a database that has all the components we use, that has the failure rates for different design profiles and operational environments, hopefully verified with field failure data. We need to know the component failure modes for every component. We need to know the failure mode distributions for every component. And we really need to know, especially for functional safety and for manufacturing and corporate liability and warranty economics. We need to know the useful life. Of all the databases that were studied by exida and myself, we found that IEC TR 62380 provided a lot of what we needed. It was a good start, but much more was needed. And so in general, we find that internet research, technical papers, component books, published books on component manufacturer meetings, gathering field failure data and studying it, and IEC TR 62380 were all required to generate all the information needed for an FMEDA. Now, those distributions will vary for mechanical components because there is no equivalent of IEC TR 62380 to start from, but you can still do all the other stuff and build a good database with a lot of engineering effort over a long period of time. Now, all reliability engineers understand that the root source of data, the primary ultimate source of data, is field failure data. But it's hard to find, and there's not that much of it, and it most often does not provide the level of detail that we need. Therefore, one technique that we've been using is to compare FMEDA predicted results for a total product where we can get failure rate data to the FMEDA results. Whenever the field failure data did not match the FMEDA prediction for a given environment, an investigation had to occur. And over many years, we discovered we needed new components, we needed to update the components, and we needed to add new failure modes and distributions. This is basically a closed loop feedback system that can be used over a longer period of time and a lot of work to update component failure rate and failure mode data. We have a whole webinar on this subject. If you're interested, look on the exida website. But I can tell you that after over 15 years of comparisons in field failure studies, comparisons of field failure studies and FMEDA results, it's getting pretty realistic. Now, the average FMEDA result from a number of different FMEDA designs represented by these little blue diagonals generated a failure rate of roughly 520 fits, and that compared to the IRITA field data of 410 and the Dow field data of approximately 480. So the bottom line is this calibrated database is generating numbers that are pretty close, but somewhat pessimistic. And that's kind of important. In other words, a slightly higher failure rate. Now, the problem with average is that average failure rates will penalize some situations and underrate others. I don't think penalizing is a problem in safety design because perhaps the system designers will over-design a little bit too much safety. But the other side, we may have to take a more detailed look. In other words, sometimes there is a need for more detailed and accurate failure rates. Now, it's absolutely possible to do a more detailed inspection, a more detailed review of the design strength and the device application to generate more realistic failure rates. And there are models for site-specific failure rate that can be applied typically at the systems level. What am I talking about more detailed analysis? Well, for example, a design for a microcomputer board had a massive heat sink as the cover of the module. In effect, there was a thermal short circuit between the lid of the relatively high power dissipation microcomputer chip between the chip surface and the massive heatsink. Thermal testing indicated this particular surface temperature dropped by approximately a little over 30 degrees C. Those of you who are reliability engineers know that what a big deal this is. And it'll have a significant difference. So this particular design had this feature added to give it higher design strength. And we can evaluate that and use it to adjust the failure rates of that component. There are many things that can be done. Look at this list. Coating on PC boards to protect against humidity and corrosive atmospheres, if there are such things in the intended environment. There's a lot that can be done to protect against electrical transients, power surges, and electrostatic discharge. We can use higher design margins in the component, pick higher quality components. I have to smile about that because I learned some of these lessons the hard way. I guarantee you now we're going to pick really good electrolytic capacitors if we need them at all. We can add physical protection. You can specify special surface finishes on mechanical parts. And you can certainly select stronger materials like elastomers and O-rings and so forth. The particular design strength analysis, by studying and documenting exactly what was done to a design, in combination with formulas to adjust the failure rates, can show the direct impact of design strength analysis. I'll come back to this in a minute, but I talked about operational and maintenance characteristics. And one of the reasons I'll just hit that again is a lot of reliability engineers have never imagined that the failure rate is different from site to site. But as I said, the failure rate can vary by 4 to 10x. That's a big deal, maybe the most significant variable of all. A site safety index model is a very simple approach. You can read all about it in a series of white papers and technical documents on the exida website. But it evaluates a number of criteria about what is done at a particular site. And there's a questionnaire and an evaluation method that can be used to categorize the site safety into one of 5 categories. SSI 4 is probably not realistically achievable because maybe. I have seen a nuclear installation where they probably reach SSI 4. However, most of the time, we consider SSI 2 as average. What you need to evaluate design strength and specific environmental parameters is an FMEDA tool where you can change operational profiles and automatically update results. There are many things you need in an FMEDA tool, and there are many available on the market. The one I know the best, obviously, is the one from exida, FMEDA-X. There are many available. You can pick the tool that suits you the best. So I conclude, a great way to start is using average component reliability failure rate data validated by field failure data comparison. And it can provide realistic, but if it's well calibrated, if it's well calibrated for functional safety, it'll provide somewhat pessimistic results. But they're average. An FMEDA tool that can recalculate results for different environmental profiles and applications can allow an FMEDA to be more accurate for very specific applications. And sometimes it's worth the extra engineering effort, the extra analysis effort to do that work. Specific models are typically done at the installed systems level. And if you apply such a model, the failure rates can be adjusted to specific operational maintenance situations. The real problem with that is if you're designing a product that's meant to be used in a wide number of different applications and a large number of sites, you can't do that. So it's typically not part of an FMEDA tool, but can be applied at a systems level where a specific bespoke system is being designed for a specific site. FMEDA analysis is valuable, but the longer it takes and the more it costs, the less valuable it becomes in the world of product development, where trade-offs must be made. And I know that when I was managing projects, costs and schedules were quite important to my marketing department and my management. So FMEDAs should only be done to the level needed. Now, I'd really like to know if anybody has any questions. Anybody see anything? Questions or comments are all welcomed.
There are a few questions here, Bill.
Go ahead and give me, read a couple out. Pick some good ones for me, Kristen.
Sure. Is there any standard to follow in order to get realistic field failure data?
No. The problem is standards typically take years. Failure data changes sometimes several times a year. I'm not convinced. Well, I have seen clear evidence. IEC TR 62380, a number of very competent engineers did a great job, but they simply could not keep up. And that particular standard was withdrawn by IEC. And I don't really believe the concept of a standards body has the flexibility and speed to keep up with electronic component failure rate data. Thanks, that was a good question, thank you. Another?
Let me see here. I have not seen any references on conformal coatings MIL standards as it relates to the SSI and the FMEDA.
Conformal coating is done to protect against things like humidity and corrosive atmospheres. The result of that must be determined by testing. On the projects I've been involved in, corrosion testing was done, and we had results that showed us specific rates of corrosion and how they were reduced, and we eventually translated that into a lower failure rate via our own test results. That's all I know of, and that's all I've experienced. And I don't know of any, I just don't know of any recent standards on that. I still believe it's very valuable, however, if it's worth the cost.
I have a question here that asks, is the site safety index model similar to the maturity model?
Actually, it very much is. The particular site safety index model we developed and are using at exida is determined by a series of questions which do come from functional safety standards. And it's just a matter of how much of this stuff do you actually do and how much do you pay no attention to. And it is kind of, I guess it's kind of realistic that maintenance budgets and other things do have an impact. And sometimes management is very focused on short-term results versus long-term results. And that is a matter of maturity and attitude. I do find them to be very similar. Any other good ones, Chris?
How do you identify if expanding the analysis from FMEA or other tools to FMEDA is better for your client? What would be the biggest benefit to convince them of the transition?
Well, there's no real transition. You must do an FME. You must do a qualitative FMEA to give you the information you need for an FMEDA. Because usually, at least in the exida model, the FMEA is at a block diagram level, done at systems level or high level hardware, software, and cyber design. Qualitative. Purpose: identify block failure modes and identify all design mitigation mechanisms. Now, if you take an FMEA further and add the, I'm trying to remember that, and you go to the FMECA methodology where you add criticality, likelihood, and magnitude, you're still semi-quantitative. You get a number between 1 and 10 and 1 and 1,000, depending on your point score. Now, we skip that stage because we're using an FMEDA to substitute for that. But the FMEDA gives you very different quantitative results. If a particular client doesn't want any failure rate predictions, then you can go ahead with an FMECA, take care of the major design problems and identify design issues and so forth. That's been well accomplished by FMECA over the years. DA actually gives you quantitative results of diagnostic analysis, or diagnostics, for example. A design comes up. Some engineer suggests, I want to add an automatic diagnostic to pulse the inputs. And the engineering manager says, well, what's that going to cost? I says, well, I have to add $6 worth of components, and it'll probably be about 200 man-hours of engineering time. How does the engineering manager or the marketing people or the corporate management know if it's worth adding that diagnostic? The FMEDA can show you the exact result of adding that diagnostic. That's why I used it when I was a project engineer, for that exact purpose. As you can if you're designing a project for functional safety, you basically have no choice. Well, there are many ways. You can use field failure data, but what if it's a new design? You've got to do something to generate failure rate predictions as a function of failure mode if you are involved in a design for functional safety. IEC 61508 or ISO 26262 for automotive. So those are the ways in which I would evaluate a client's needs. And if they just don't care about any of these things, then we don't have to go beyond a qualitative FMEA. I'll just sit back to that one slide. Because FMEDA provides a full set of failure rate metrics, proof test coverages, if that's involved, useful life, and proof test effectiveness. Any other questions?
I have quite a few that are coming in.
Well, pick one more and then we'll answer all the rest. I'm very happy you've got these questions coming in. We'll do another one and then we'll answer all the rest with some emails to everyone.
All right. Let me see here. Does FMEDA extend to the finish of a product, i.e. the housing, as opposed to the function of the product?
The housing can have an effect on failure rate, but not, I'm not sure about the finish, unless the finish impacts thermal conductivity or provides protection against humidity, environmental corrosion, and so forth. All of these things do have an impact. The formulas that are used to generate the failure rates in the FMEDAX tool, they cover humidity because humidity results in corrosion, which often results in short circuits between pins or between unprotected circuits on a circuit board, although it's mostly between pins and solder joints and so forth. So if the housing is sealed, you can take credit for that if you're doing more detailed analysis. And if there are any mechanical parts involved in the design, you need to include those for functional safety if they are part of the safety function. Often the housings have a whole lot to do with how mechanical parts operate. Good questions. Thank you so much. If you have any other questions later, don't hesitate to send in an email and we'll do our best to answer your questions. If you need more information, please don't hesitate to look at the exida website. I hope you found the information valuable. Look at the exida website, take a look at our other webinars and our courses. Thank you all very much for your time.